All right, recording is rolling. It is Wednesday, March 20. I want to take one day to tell you guys about relativity. You guys have on your desk these thumbnail notes for the posters over there on that wall. Here's relativity poster. On the backside are related to quantum mechanics. AP, they don't cover like every single topic that I do in my honors classes, including relativity. So take a day to at least do this. After spring break, I just want to take a couple days to electricity and circuits with you guys too. So in time. All right, so you guys get one day to learn about this. Okay. So what is relativity? Well, I'm actually going to start with just plain Newtonian relativity, which is nothing crazy, but just to have a place to start. It's eventually going to lead to. But when people say relativity, they're really talking about Einstein relativity, which gets crazy wacky. And by the time we walk out of class today, I'll put those thoughts in your mind about that. And so let's just start with plain Newtonian relativity. Suppose you can stand on still ground and throw a baseball at 30 meters per second. Right? And this guy's got a radar gun. You guys see that radar gun right there? You stand still ground. What speed is that radar gun reading? 30 meters per second. Right? Straightforward. Right? Now, what if you hop in the back of a truck that's going 20 meters per second, and then you throw the baseball also at 30 meters forward? Now, what's that radar gun reading? 50, right? So 30 plus 20 is 50. What if this guy throws the baseball back the other way? Now, what's the radar gun reading?
-10.
Oh, negative sign. I like that. You got the negative sign for velocity, right? Yeah. There you go. That'd be true, right?
10 backwards.
Yeah, 10 backwards, right? There you go. Okay, so that's just plain Newtonian relativity. So that's all fine and good, right? Okay. Also, another idea. Do you guys remember one of the first points I ever made? This goes probably back to like August, right? Is if you're sitting blindfolded in a car and your friend's driving the car, can you feel how fast the car is going? And you guys said no, right? You can feel accelerations. You can feel it speed up, slow down, or steering wheel. But can you just distinguish the difference between like 50 miles an hour versus 70 miles an hour, just constant velocity? No, it feels identical, right? Okay, now hold on to that idea too, because that's going to come back in a few minutes, right? So let me give you guys a little bit twisted version of this. But let's say there's a couple of boaters. You guys see a couple of people in boats, and they got little paddles, right? And let's say they've been racing back and forth across this lake, and they're like tie all the time. They're about the same. They both paddle at, let's say, 10 meters per second. I'm just throwing some numbers on the board here. It's kind of crazy fast, but let's just run with it. It's nice round numbers. 10 meters per second, they can paddle. Right? They say, hey, let's do this. Let's have one of us be in this lake where the water's not moving, and let's have this other guy jump in the river. You guys see the river's flowing downstream at 5 meters per second. Here's what we do. See that tree way down there at the other end of the lake? We're gonna paddle all the way down right, to that tree, and then paddle all the way back. Now, of course, the guy in the lake, he's just going back and forth in still water. But the guy in the river, well, now you have to consider relative velocities, kind of like the baseball in the truck and the guy with the radar gun, right? We got the guy paddling relative to the water, we got the water relative to the tree, and now we got how fast this guy going relative to the tree, right? So now we're juggling it's three different perspectives. Right? So question for you guys though is who wins the race? Again, I threw some numbers on there, but I could have made any numbers. Right? And there is a universal answer to this question, right? Regardless of what numbers I throw on the board. Okay? Let's see, show hands. What are you guys thinking? Right, so here's your options. Either the guy in the lake wins the race to the tree and back. Right? Did I mention that? It's a two-way race. Right, so we're going to the tree and then we're going back to the start-finish line, right? Or does the guy in the river paddling downstream and then paddling upstream, right? Okay. Right. So who wins the race? And somebody does win. They don't tie, right? They never tie, right? So show hands. How many guys say the guy in the lake wins? The guy in the lake. Right? Who says the guy in the river? Okay. So I'm seeing it's about 50-50, about right, half. Right? So I ran the. How would you solve this mathematically? If you're trying to see who wins a race for some set distance, you're going to compare maybe how much time it takes to complete the race, right? So I went ahead and solved that here. Doing fast for a little bit. Distance equals speed times time. Therefore, the time is how far I have to go divided by how fast you're getting there. Right? Now, for the guy in the lake, he goes 120 meters one way, 120 meters the other way. Let's say same speed. It takes him like 24 seconds. Right? The guy in the river, well, one way is getting a boost from the current. 10 plus 5, that's 15 meters per second. But the other way is fighting the current. 10 minus 5, that's like 5 meters per second, the opposite way. Right? It comes out to 32 seconds. So you guys see the guy in the lake wins the race. Right? You see that? Right? So the guy in the lake wins the race. Right? Now you can kind of extrapolate that a little bit. If you're racing somebody and it's going to be close, generally speaking, if you pace yourself, you tend to win the race versus if you like sprint and then get winded. Right? It's similar idea. Okay? Guys get that? Okay. Again, this is all just Newtonian relativity, nothing crazy, right? Oh, okay. But now we're about to break out some crazy. Right? Well, almost. Right. We're gonna go back to 1849. 1849. There's this guy Armand Fizeau. He was over in Paris, I think it was, and he says, "Hey, I want to figure out what is the speed of light." There's been a question kicking around for just a couple thousand years. What is the speed of light? And he figured out how to do it. And figure out how to do it with this cog wheel, this toothed wheel. So here's his experimental design. Says I'm going to set up some light source I'm representing with a candle, right? And then I'm going to set a mirror way off in the distance, that maybe it's like 5-10 kilometers away, just crazy far away. It's like across town, right? Okay. And here's an observer represented by an eyeball, and he's watching the reflection of that light source, right? So he sees the reflection bounce off the mirror. So maybe it's like a few kilometers that way, and then a few kilometers back, sees the reflection. Okay, listen. Okay. All right, now let's insert the cog wheel, the tooth wheel. He's going to give it a spin, right? Now any light beam that goes through the gaps, well, any light beam that hits a tooth never makes it to the mirror in the first place, so you wouldn't see the reflection. Right? The beams have to have gone through the gaps in the teeth and come back. But what if this wheel is spinning so fast, so crazy fast, that any light beam that had happened to go through the gap, by the time it bounces off the mirror and comes back, it will be hitting no longer a gap, but now a tooth. Now it's hitting a tooth because there's a tooth where the gap used to be, right? Which this doesn't have to spin very much, right? You guys see that little sliver there that I've labeled theta, right? Each tooth is now taking place of a gap, or a gap is now in place of a tooth, right? So this only has to turn maybe just a couple of degrees, maybe, right? Depending on how many teeth you have, right? But it would have to be spinning crazy fast because for light to bounce to the mirror and back happens in an extremely short time period because light travels so fast, right? Right. Now, what do you notice? He spins it faster, until he reaches some omega, some angular velocity, that what appears, it looks like there's a door closing on the reflection of this light source. And when he has it, bam, match, he knows that he's able to, at that point, calculate speed of light. Like everything's lined up, right? So got these 3 green boxes set up, right? So 2 times the separation distance, there's light bouncing back and forth, right? Is speed times time. Now this is special speed, this is speed of light. I'm calling it C. That's ultimately what we're trying to solve for. It's the very bottom box says C equals something, right? What else we got? How far does the cogwheel turn during this whole process? 2 pi radians would be one complete revolution. We're going to divide by 2 times the number of teeth, right? Suppose you had, however many teeth you have an equal number of gaps. And you just need this to turn just enough so that tooth covers an adjacent gap. That's why it's 2 times the number of teeth, right? To take one full revolution, divide by 2 times the number of teeth, that's this little sliver, how far it turns in radians, right? Also, angular displacement is angular velocity times time. This is the time to, again, bounce back and forth, right? You can do a bunch of substitutions, do some algebra, and you get this expression here for the speed of light. If you know how fast you're spinning it, that's what omega is in radians per second. Right? And, or how far away is the mirror, how many teeth on the wheel, pi is 3.1415, or 2. You can calculate what is the speed of light. This is the first time the speed of light was really accurately discovered. I forget if I told you guys, there was another story. It goes back to, I think, the 1600s. There was a Danish astronomer who was watching Io orbit Jupiter. That's one of the moons of Jupiter. And there was like a Doppler shift. He was able to kind of get a ballpark idea for speed of light, right? But this is like really a modern accurate value of speed of light. 3.0 times 10 to the 8 meters per second. He was able to figure out 1849. Okay, so that's all fine and good, right? Right. Everybody's good so far, right? Right. Now, what does light travel through? Did you guys maybe learn in some science class light can travel through the vacuum of space? Right. That's how light gets from, say, the sun to Earth, right? Now we know that modern day, but they didn't necessarily know that back in 1849. The prevalent thought that back then was, well, we know that light's a wave, therefore, and we know waves need some medium to travel through. What was the thought, right? Like, how are you guys hearing me right now? Is there a sound wave going through the air? Right? If you vacuum out all the air, you wouldn't really be able to hear me, right? Right. What about like a pulse on a rope? Right? You send a pulse on a rope. Right? The rope is like a medium for like a wave to travel through. Okay. Now, how do we know light is a wave? Well, one way is something called the double slit experiment. If you take a card and put a couple of slits through it, right? Now, if you put this in like a tank of water and put some ripples through, so Huygens principle, each ripple of water will go through each one of these, right? And then it'll send out like wave, like here's crest. If you look at it from the side, like crest, right? Okay. And then these 2 wave crests would interfere, and then on the back wall, you get like an interference pattern, right? Well, you shine light through a couple slits on a card, and it also creates an interference pattern. That's maybe strong evidence that light has wave properties, right? Here's another, I can do an experiment right here to show you guys that light is not specifically a wave, but specifically a transverse wave. Right? I have two polarizing filters. Did I show you guys these before? Polarizing filters, right? These only let light through in one direction. Right? You might have polarizing glasses possibly, right? So maybe like vertical and vertical. But what if I turn one of these 90 degrees? Vertical and horizontal. Ooh, look, it blocks all the light. Right? That only works specifically with transverse waves. Right? Like right now, you guys are hearing me because of a sound wave that's longitudinal. That's like a pressure wave, right? Which light is not, right? These polarizing filters only work. Okay, so we got this. We got this. Right, now, what was hypothesized again back in 19th century was that there'd be something called this luminiferous ether that light would travel through. Right, maybe that's the medium that carries light. Is what people were thinking back in the day. Right? Now, if you've never seen that term before, especially in a science book, that's probably a good thing because I'm about to walk you guys through this experiment that unintentionally disproved this idea. Right? They're thinking about these like relative motions. Right? Say, okay, well, there must be a medium for light to travel, right? Right? That would make sense, right? And what would be the speed, the relative speed? They're thinking about Newtonian relativity, right? Back in this before Einstein published this anything. Right? The relative speed of Earth compared to this luminiferous ether. Now, why would they think that there was such a thing that they could discover in the first place? I'm drawing you guys a picture here. So, here's the Earth, right? Earth, equator, North Pole, South Pole, right? And the Earth is spinning so fast that if you're standing on the equator, you're going about 1,000 miles an hour compared to the axis of the Earth. Okay? That's not the end of the story either. The Earth is also revolving around the sun, right? So there's a huge like west to east velocity, right? Compared to like north south, the Earth isn't really moving north south, but east west or like west to east, it's rotating, it's spinning on its own axis, and it's also revolving around the sun. So if you're thinking about like relative motion and you think back in 1800s that there's some kind of luminiferous ether, right? Then there should be like some kind of relative motion, right, for like light to travel on that you could detect, right? Kind of like this, right? What if you took that cogwheel experiment, right? Like Friso's cogwheel. Right? Here's the light bouncing back and forth. What if you have this east-west versus north-south? Right? How would that be different? Like if you bounce it east-west, that's aligned with the motion, like the rotation and the revolution of the Earth. Versus if you bounce it north-south, well, that has nothing to do with that type motion. So that's kind of like the guy paddling in the river, east-west, versus the guy paddling in the lake is more like north-south, right? You're going to get different relative speeds, right? And okay, you guys get that? Right? Like the guy paddling in the river overall comes in later, so he had like a overall slower speed, right? Something like that, right? So that's what they're thinking. Right. So let's bring in back to Nicholson Morley here, 1887. Right? So their setup is we're gonna have this light source. We're gonna send out light rays in all directions. We're gonna focus on one ray of light that say heads towards this configuration. I got this half silvered mirror, this beam splitter at a 45-degree angle, right? And half the light goes through and half of it boing reflects off. Right? I got a couple of mirrors that are equidistant from that 45-degree angle mirror. Light bounces off there and then goes through and eventually reaches this observation point, right? Represented by an eyeball, got an observer here. Right. Now, what they're thinking is, suppose this is like east-west and this is north-south. Again, east-west is like the guy in the river paddling one way and the other way. One way is with the current, the other way is against the current. Overall, he's going to be slower. Versus north-south, well, that would be like, kind of like the guy in the lake, right? It has nothing to do with the spin of the Earth, right? So maybe that'd be like overall faster. And you would expect, therefore, these two beams are going to enter it slightly out of phase. If they're out of phase, here's a couple of transverse waves, right? You would see to take that in an interference pattern, you'd see that. But that's not what they saw. The first time they ran this experiment, they got those two waves were exactly in phase, which was weird. That was not what they were expecting at all. Like, okay, this is weird. Right? But hey, what if we just do this at a different time? What if we do this 6 hours later, 12 hours later, like day versus night, maybe it can make a difference. Hey, how about summer versus winter? What if the Earth is on the opposite side of the sun, right? Compared to this luminiferous ether that everybody's thinking exists back in 1800s. You should see something. But it didn't matter. It didn't matter how they did. They always got the same speed of light no matter what. Right? So this is strange. So this luminiferous ether does not exist. Light can't travel through a vacuum. Right? Now think about maybe another implication of this is what if think of something that uses light. Let's say like a microwave oven, right? That's microwave, so it's like it's not exactly visible light, but it's the same EM spectrum. You just stretch it out longer wavelength, right? Well, if you're at rest or if you're like in a plane moving really fast or in a rocket or at different latitudes on Earth, right? It's going to work regardless, right? It doesn't care, right? It's kind of like being the passenger in the car that your friend's driving. You don't know how fast the car's going because you can't physically tell the difference, right? Right. So So how would light like know if it's like along to the right or whatnot? Anyway, so these conflicting ideas, but they seem to accidentally just prove this luminiferous ether idea, right? And what goes hand in hand with all this is that the speed of light is the same regardless of your relative motion, right? Now let me show you guys like how bizarre an idea that is, like especially back in the 1800s when they weren't expecting this. Let's go back to uh, um, right, back to this guy throwing the baseball, right? Right. So get into this this radar gun text. Okay, so we've got 30 meters per second versus 30 plus 20 is 50, or 30 minus 20 could be 10. Right? But what if we replace the baseball with a light beam? And let's replace this truck with like a rocket, right? What if you're in a rocket, right, and you send out a light beam? I'm going to draw it just to emphasize this point. And so I got a rocket, right, going really fast through space, right, and sending out some light beams, some headlights or something crazy, right? Right. I got a guy inside the rocket, and I got a guy like standing on the surface of a planet watching the rocket whiz by. Right? Let's say they both measure what is the speed of light, or maybe they both break out a couple of cogwheels, Fizeau's cogwheels, and they get ascertain what is the speed of light here, right? For this guy versus this guy, right? Let's have the rocket go crazy fast. Let's say this rocket, so I'll say V rocket, right, is like half the speed of light, which is crazy, but just to run with this idea, right? Half the speed of light, the rocket's going, right? Now, um, it's sending out beams. Now, how fast do you think these light beams are going? How about the speed of light? C, right? So C, the speed of light, right? Uh, but in whose frame of reference? Like if you're in the rocket, do you think these, if you broke out the tooth cogwheel and you measured what is the speed of light, do you think you would get exactly the speed of light? Yep, you get exactly the speed of light, right? The whole 3.0 times 10 to the 8 meters per second. You get exactly that. What if you're this guy standing on the planet watching the ship go by, and somehow you also get the speed, right? Do you also get exactly the speed of light? Yes, you do. Yes, you do. You guys see how weird that is? Right? That's like if I go back to, like, if it worked that way for the baseball, then this guy in the moving truck and this guy's on still ground, this radar gun would be picking up the same speed for the baseball. Okay, right, which is not how Newtonian mechanics works. Right? But somehow for light, everybody gets the same speed of light regardless of their frame of reference. Right? Is that right? Which is again like absolutely bizarre. People weren't quite sure what to make of this, right? Until Einstein comes along, right? And Einstein cracks this puzzle. He says, "Ah, I figured out what's going on." And so here's a relativity train. Or, I don't know, maybe I should have made this a rocket. I think it would make more sense. But right, you've got some guy in a red hat inside a moving vehicle, and some guy in a green hat just standing on still ground. And let's say, right, this moving vehicle moves by. Right, right. So, so thought experiment here. Let's put a light source on the ground, represented with a flashlight, and we're going to follow one ray of light, a light beam that bounces up. Oh, there's a mirror on the ceiling. Look at that mirror on the ceiling. Boing, and the light ray bounces up and down. Right? Now, if you're inside the vehicle, inside this train cart, as long as it's traveling at constant velocity, you might not even know that it's moving. Right? Whether it's at rest or moving, you cannot distinguish the difference inside the car. Is that true? Right? Right? Just like being blindfolded in the passenger seat of a car, I-95. You don't know how fast. Right? So from your point of view, all the light ray does is just go straight up and down. Right? That's it. Right? And maybe that's exactly what's going on. Right? You may as well be at rest. Right? It just goes up and down. But to a guy outside watching the train car go by, the light ray does not, in fact, go straight up and down. It actually goes on a diagonal path, right? So that's what this guy out here sees. Like that, right? Right. But again, if they each measure the speed of light, they would get exactly the same speed of light, even though these light ray travels different distances, right? Like if I cut this trip in half, right? Just kind of focus on triangle here. You guys see like a right triangle here? Right triangle, right? Right. Just cut the story in half, right? From the floor to the ceiling, the guy inside the train says, well, it only traveled like straight up. The guy outside the train says, no, it went along this diagonal, right, which is the further distance. It's hypotenuse of a right triangle is along the side of a right triangle. Right? So they see the light ray go different distances, but at the same speed. The only way to reconcile that is that these two guys must be experiencing different passages of what? Time. Ah, all right, hence I got little clocks going on. Ah, it's at different times, right? So this is something called the twin paradox. Twin paradox. If you start like say two twins, they break out. Let's say these are like atomic clocks. They're measuring down to the nanosecond or whatever crazy, right? Right. And they're exactly aligned clocks, right? And then one guy hops on board, right? And then you set him in motion. Let's say at a relative speed. Oh, here's exactly the speed of light. This is like the definition of the speed of light through a vacuum. Right. Oh, yeah. Turns out that if you start from rest with the guy in the green hat, right, but now you're on the red hat, right? He's doing right. That time has to slow down in your frame of reference relative to the green guy. And this guy in the red hat gets off the train, and then they compare clocks. And more time has passed for the guy that was at rest than the guy who was in motion, right? And he had to accelerate to get in motion in the first place, right? Now, if you're along for the ride, you'll never notice anything weird about your own local environment. So you don't see your clock speeding up or slowing down, or I guess slowing down, right? It doesn't matter how fast you go. You can go like 99.9999% speed of light. You'll never notice anything weird yourself, right? But if this guy in the green hat is like looking through a telescope or like looking through the window, right? It looks like this guy's clock is speeding fast, and vice versa. This guy could be looking out the window back at this guy and sees his clock speeding fast. So the green clock is speeding fast, and the red clock is speeding slow, right, relative to each other, right? Now you can find this mathematically with just Pythagorean theorem, right? So you guys see I set up this triangle right here, right? This vertical leg of the triangle is perceived by the guy in the red hat. This diagonal perceived by this guy in the green hat, right? And how far the train moves, these are all distance values, right? How far the train moves, the speed of the train times time, that can only be detected by the guy in the green hat, because only he knows how fast the train's actually going, right? So you put it all together, Pythagorean theorem, that's Pythagorean theorem right there, isn't it? Right? What I might want to know is, well, what is one time in terms of the other time, right? Like if you know one clock time, what's the other clock time? And this is the answer right here. Right? So this is called time dilation. Time dilation. Right? Now this is a really subtle effect for most cases, right? So what is from here on out, I might refer to the red hat guy as rocket twin and the green hat guy as earth twin. Right? So if you hear something called the twin paradox, you can look it up, right? The twin paradox, right? So got rocket twin on the rocket and earth twin just hanging out on Earth, right? So what is rocket twin's time compared to earth twin's time? Right? Right. Well, so you can take one time and divide by see this square root fact. It's called the Lorentz factor. It's the Lorentz factor. Right? Now let's run maybe some ideas here. Right? What if first of all, what if the train's just at rest? What if the rocket's at rest? Would B be 0? Let's try this out. What is 0 squared? 0 divided by c squared. 0. What's 1 minus 0? 1. What's the square root of 1? 1. T naught divided by 1 is just itself. And hey, the two clocks align, right? That's called the correspondence principle. So if you ever come up with some crazy new theory about how the universe works, like Einstein did, Einstein was replacing like hundreds of years of Newtonian physics, right? Then at least the correct results of the old theory have to like also show up in the new theory, right? It's called correspondence principle. You see that there, right? And now what's the fastest that any human is moving relative to any other human, like right now? I'm gonna guess it's probably someone in the International Space Station, right? And to stay in orbit, low Earth orbit, you have to be going, let's call it about 8,000 meters per second. You guys remember that, right? From Unit 3, about 8,000 meters per second. That compared to the speed of light, 3 times 10 to the 8 meters per second, right, is so relatively small. If you run the numbers here, this fraction right here is almost 0. So 1 minus almost 0 is maybe it's like 0.999 something, right? So is there time dilation? Yes, but it's so subtle. You would really need atomic clocks on the International Space Station to see the effect, right? And I think they have done that, right? They do see there's a tiny mismatch, right? But even if you were like in communication, like in Houston, and then calling up to the astronaut, right? They wouldn't notice any kind of lag from this relativist effect because it'd be so subtle, right? But this does matter. Like this isn't just a theory with no purpose, right? You guys probably all use GPS in your phones, right? GPS, right? Let me cut kind of to the end of this because there's a lot more I want to tell you, but just to zoom ahead a little bit, right? GPS, global positioning system, actually does require a theory of relativity. So it can be like the Earth, right? There's a bunch of satellites going around, right? And then your phone is picking up signals from all these satellites. All these satellites are sending signals, right? And if the satellites know, say like where they, so we got distance equals speed times time, right? We got speed of light, right, which is universal constant, right? And if you know how much time it takes for those signals to reach your phone, then you figure out what is your distance. Now, if you know your distance from one satellite, then great, you've narrowed your location on there down to like a circle, right? But if you know your distance from 2 satellites, okay, well now it's got to be like one of these 2 points. If you know your distance from 3 satellites, now you can like zero in and you can target your exact location, right? But those satellites are moving so fast relative to Earth that there is a tiny special relativity effect. There's also the fact that they're in weaker gravity field. I haven't even mentioned general relativity yet, but gravity also slows down time. Is kind of way to say it, right? You need to take both those effects into account. And if you did not take relativity, like theory of relativity, into account, GPS would not work. It'd be off by like thousands of meters per day. So it would just not work. Right? Or we'd have to adjust the clocks and not understand why we had to adjust the clocks. Like, why do clocks tick differently up in space? Right? It's really subtle, but it's enough that it makes a difference. Right? So you guys good so far? Right. So you go into motion. Time does dilate. Right. And just to round out this twin paradox story. Right. So to give you guys a twin paradox story. So 2 twins start off both on Earth. One guy jumps in a rocket, and let's say he goes like 99 point something percent the speed of light, just almost the speed of light, crazy, right? Right. And it comes back like a year later to him. He says, I've been flying around for a year. And he meets up with his twin brother. His twin brother, I've been waiting 20 years. So his brother has like a full like gray beard. He's been waiting 20 years. And the guy in the rocket said, it's only been a year, right? Right. So got a mismatch in time. Okay. All right. All right, so here there's time dilation. Now, it turns out that time is not the only thing that dilates. There's also these other dilations and contractions that go on. Right? Let me hit a length contraction, show you guys why that one would also have to be consistent with it. Right? Let's say we're going from Earth, here's Earth, right, to some distant solar system, like way over here. I'll call it solar system B. Maybe it's way off, right? Let's say it's like distance equals 10 light years, right? Just to throw a number on the board, right? Like 10 light years away, right? We're going to get in a rocket, we're going to take off, and we're going to get to that distant solar system, right? Right. Now, if you sent like a radio wave, it would take 10 years to reach it, right? And if you send a communication signal back, it would take 10 years to cross it, right? So what if we got this rocket up to like 99% the speed of light pretty quickly? Just simplify the numbers, right? Then it would take at least 10 years to get to the solar system. That'd be true, right? But don't forget this time dilation effect. If you're along for the ride in the rocket, you might think that whole process only took like a year, right? So you get to the solar system B, you're like, oh, hey, I just crossed 10 light years in 1 year, right? Well, hold on a minute. What you might see too is that there's something in physics, there's a universal speed limit, cosmic speed limit. You can't reach the speed of light, right? Can't reach the speed of light, because if you did, what would that mean? Like for this fraction here, right? Like if v is greater than c somehow, let's try v equals c. What would happen at the speed of light? Guys, what is c squared over c squared? Is that 1? What's 1 minus 1? 0. Square root of 0, 0. Anything divided by 0, is that undefined? Just blows up, like asymptotic? Right? So you can never quite reach that speed, right? So how do you go 10 light years of distance in just 1 year, right? Well, it's that time dilation effect. If you radio into someone on Earth and say, oh yeah, it definitely took at least 10 years to get there, right? But on the rocket, you think that only took like a year, right? Because from your point of view on the rocket, it's not just time that dilates. There's also length contraction involved. So now we're taking those distances and we're making them shorter. And this Lorentz factor here, this whole square root, is bound to be, it's always bound to be between 0 and 1. Whatever you plug in for v, right, between 0 and c, this whole square root factor is somewhere between 0 and 1. Right? So you're taking a 10 light year trip and you're, say, multiplied by 10%. Right now it's only like 1 light year worth of distance. Is that right from your point of view? Right. And another dilation that happens is this momentum dilation. Sometimes you see it called mass dilation. Right. So here's that momentum will also increase. Now this is something that scientists see all the time. You guys know Large Hadron Collider over in Switzerland, right? There's this huge synchrotron where they speed up. They'll put like hydrogen atoms in, and they'll speed them up near the speed of light, like 99.9 something percent the speed of light, right? And they'll steer it around this huge synchrotron. It's so big it actually goes under the border with France, right? With the magnetic fields, which I'm going to represent with like a horseshoe magnet. Really, it's like magnetic fields all the way around. Okay? And hey, that's providing like a centripetal force type, isn't it? To keep it in a circle, right? And the more momentum the particles have, the more force you need to keep it in, right? So they might put in like a gram of particles, and then as they speed up like close to the speed of light, they say, hey, it looks like there's like 20 grams of particles. Like where'd all this extra mass and momentum come from? Against a dilation effect from the special relativity. You can calculate exactly what's going to be from this one right here. Right? I did do a graph version of this. This is momentum versus speed. You could do time versus speed, and it would look like the same looking graph, right? Because here's the equation, here's the graph, same idea, right? So how much momentum do you have from your mass to your velocity? Well, what Newton said, it was just mass times velocity. You guys remember that? Unit 5, conserved during collisions. Momentum is mass times velocity, right? Einstein says, well, at non-relativistic speeds, that's pretty close to true. You guys see, here's Newton in dashed green. Here's Einstein in the solid red curve, right? So for non-relativistic speeds that are like, let's say less than 10% the speed of light, they pretty well align, right? But if you're pushing like 90% the speed of light, well, now there's going to be a huge difference, right? Because Newton says it's just mass times velocity. Einstein says no, it's actually going to asymptotically like take off to infinity. Right? You guys did too, right? Right. And same thing for time. If I just replaced momentum with time, now you could have the same type curve, right? Which maybe raises the question: what would it be like to actually travel at the speed of light, right? Which photons do, right? Actually, anything that does not have mass has to travel at the speed of light. So what would that be like from their perspective, like the perspective of photons, right? And from the perspective of photons, well, this heads off towards infinity. So you could say like all time happens at once, like the entire life of the universe just like goes by in a blink. And also here, if you look at length contraction, I should have made a graph for this length contraction too, but this will look at the equation. Okay. Let's say what would happen to distances from the point of view of photons. Guys, if you plug in C for V, so V equals C, right? This fraction is equal to 1. What's 1 minus 1? 0. Square root of 0, 0. Any distance times 0 is 0. So the width of the entire universe is just 0. There is no such thing as space from the point of view of photons. Ooh, that's weird, right? If you're a photon, you wouldn't actually experience space or time. Okay, here's you might come across this at some point called Minkowski space-time diagram, where let's see where we are. Got about 5 minutes. Right. Oh, so I made like a 3D looking version of this. X and Y axis is supposed to represent spatial dimension. There's a simplified version of this too, where sometimes they just have one axis for the spatial dimension. Right? And then the vertical axis here, think of this sort of like representing time. A lot of times you'll see it as the speed of light times time, so it's all spatial dimensions, and you can draw this 45-degree angle here. But think it's basically time. So if you're just sitting at your desk at rest, you're not moving through space, but you are moving through time if you're sitting at rest. So you're like moving up here, right? Now, if you do move through space, the faster you move through space, then the slower turns out that you move through time. That's like twin paradox time dilation, right? And the closer you're getting to this this dashed line at the 45-degree angle, which would be the speed of light, right? Now, again, you can never reach that dashed line. It's why I dashed it. It's like an asymptote, right? Something like that, right? And the only things that can ever affect you, like where you are right now, has to be in this cone that I labeled past, and anything that you can have an effect on is going to be in this cone in the future from where you're sitting right here. Right. So like if you look at that picture of that Hubble deep field, that's the edge of the observable universe, right? Nothing there can really affect you like right now, unless there was like a light wave sent off like a long time ago that would somehow land in this this green cone, right? Like there was an alien civilization that's sending light wave like a billion years ago or something crazy, right? Right. From the mass dilation, you can actually derive this mass energy equivalence. You guys have probably all seen this, right? E equals mc squared. Right? So this is mass energy equivalence. This is the energy of nuclear reactions. Now, when you guys took chemistry, you guys probably learned conservation of mass, add up mass of all your reactants, add up mass of all your products. It's always going to equate for a chemical reaction. Now, a nuclear reaction is not a chemical reaction. Nuclear reaction, you're changing the mass. So if you have like 100 kilograms of like uranium, and then you put through a nuclear reaction, I'm just making something up. Let's say, with like 99 kilograms. So it's like a difference of 1 kilogram. If you take that difference of 1 kilogram, multiply by the speed of light squared, which is a crazy big number, then you'll get how much energy that represents, right? And just to hammer home that point, and we're doing like a real crash course version, so I won't run the numbers with you guys, but if you did, for sake of argument, suppose you took like a little tiny mass, like the little, smallest mass in the kit of masses that you guys get, the mass box, right? If you made this your mass, it's just like 10 grams this is, right? Multiply that by the speed of light squared. They said, what rate am I using energy like living in a developed country, right? So we got lights and air conditioning and computers were running and cars were running, transportation, all the food you buy, this whole agricultural process, all the things you buy, there's some manufacturing and transportation, right? This would last like tens of thousands of years. You could supply all that energy in terms of mass, right? So yeah, so nuclear energy, getting a lot of energy, right? Nuclear energy, there's two categories. All the power plants today are this fission process. we're basically breaking apart uranium. That's not the only fission process. That's like the main one, right? Got U-235, right? Krypton, barium, right? And then like what is the I think binding energy per nucleon? Right? So if you break apart uranium to say krypton, barium, right? There's a height change on this graph. That height change is like a mass change. You can interpret it as, right? And then you can E equals mc squared, figure out how much energy there, right? But you guys see going from hydrogen to helium, that jump is like hundreds of times bigger than from uranium to like krypton, barium, right? So that's fusion. If you fuse together hydrogen to make helium, you get like almost 1,000 times the energy out of it. Right? Now, nobody's quite been able to turn this into a commercial power plant yet, right? That's still a developing technology. Although we have been able to make bombs out of this since I think 1950s, right? So we have hydrogen bombs, but not actually power plants yet, right? But hopefully, hopefully in our lifetimes, because about now. Oh yeah. Yeah, you're right. Yeah, Lawrence Livermore in California is one of the labs that's working on fusion with lasers, I think. So they have made fusion. It's just not like they need more energy in the lasers to make it than they're getting out of it. Now, actually, recently, I think in the last year, they did like through some set of numbers, like we're able to get a small net energy out of it. But I think it depends on like how you account for the energy. So it's not quite ready to make a commercial power plants yet. But yeah, again, hopefully. Well, I guess the joke with nuclear fusion is it's always 20 years away. It has been for like the last like 60 years. So, yeah. Right. Oh, right. So general relativity. So what if you bring in gravitation? So this is the way Einstein's thinking about this. He says mass warps space-time. Right. Sometimes you see like this this gridded fabric is supposed to represent three-dimensional space. Right. Einstein says we live in this four-dimensional space-time and mass warp space-time. So he has a different view of gravity than Newton had. Now, I taught you guys Newton's version of gravity, which is inverse square law with distance. So F equals gmm over r squared. Now, that works pretty good for almost all cases, but there are a few like extreme cases where it kind of breaks down, doesn't work exactly right. Also, Newton did not really have a theory of gravity. He just so mathematically it looks like it fits all these equations, gmm over r squared. Right? Einstein has a theory of gravity. He says, oh, well, masses warp space-time. And so like, why does the moon orbit the Earth? Well, it's not because the gravitational force providing centripetal force. That was Newton's perspective. But Einstein's perspective says the moon is really only moving in a straight line ever. Right? But it's moving on curved space-time, right? And that's really what establishes orbits, right? There's some experimental evidence for this too. There was a solar eclipse back in 1919. If you look that up, that was like the first experimental evidence for general relativity, right? But I'm about out of time. So there you go. There's your crash course on relativity. Hope you guys learned something. Enjoy. You guys have a good day.